What's up, guys? Welcome back to another video. I think today's episode 119. It's pretty early in the morning. It's like nearly 8 o'clock in the morning. I got to play pickleball at 9, so I thought I'd drink a smoothie and keep running through some problems. So yeah, let's get straight into it. Probably be a little 40-minute section here, and then we'll probably do one later in the afternoon as well. But just thought I'd just start pumping out some problems so I have more time for other stuff later. Some of the projects I'm working on and things like that. So anyway, we got a Sea King today. Let's take a look at the sound. Couldn't hear anything. Burp. That's our sound. But yeah, let's get straight into it. Let's check out our problem of the day. Hopefully it's a chill problem. I've already solved this one. So let's take a look. See, I prefer problems like this with a lot less words. I think the ones with a shit ton of words are just like get hella confusing, but I don't know. Let's take a look. So, given an array of numbers with n objects colored red, white, or blue, sort them in place so that the objects of the same color are adjacent with the colors in the order red, white, and blue. Only constant extra space. When did I solve this one? Jan 22, 2025. So that's 5 months ago. For array 2 pointers sorting. How will we do this with 2 pointers? Well, so low is equal to 0. Let's loop through our list. So for color in range length nums, right? We loop through. Let's take our left pointer. Sorry, let's do a right pointer here. Can we use a for loop? If we loop from I feel like this might be the only problem that we do until we leave today, but stop that. So my intuition hit. I'm thinking we can do a double here. Okay, there's going to be an n squared solution, but then we'll optimize it a little bit down. Right, so we go... Okay, we start from color plus 1. Color plus 1, right? And then we do... Okay, well, we find the min. Let's reset our min. So let's do our min is equal to... Min num is equal to, let's do float infinity, right? So we loop through and we look for our min nums, and then we do min num. Equal to min num, and then we want to pass in our nums right. Well, let's do if nums right is less than min num, then we make min num is equal to float. Then we make index is equal to, I think there's a better way to do this, but I don't know. Let's do min num is equal to nums right, and then we save the index too, because we're going to need the index. Index is equal to right. Okay, so we loop through, we get the lowest value, right? And then we move that to colors, right? So we get the lowest value. Okay. And then pretty much what we do is we do, okay, well, will that work though? I think this should work. So then we make color, sorry, nums color. No, nums color is equal to min num. Right. And then we would move, let's do temp is equal to nums color. Then we can do min num, nums color is equal to min num. Index is equal to temp, right? So we swap the numbers and then we move by 1, right? Okay, and we would simply just like return our nums. At the poker place. Okay, so what are we fucking up here? Where our output is. I feel like we're just messing up something extremely small here. I don't know. So apparently we shouldn't do this because right, we should start from the first value because the first value okay, so that was our issue. Okay, obviously our solution is slow. So I think what we might do here is we can speed this up, right? So now we did a n squared solution. So now there must be a 2-pointer solution, right? Where we can do it in place in one pass, right? Right, in range length nums. I think we'd have to do a while loop or something and compare. With a dictionary. That's a interesting way to think about it. My dictionary is 001020. I thought we had to do it in place, bro. What? And we can make an array. For we can do, okay, so should we can probably just do for I in count of nums. How can we look through this dictionary properly while also keeping track of I? I in range like nums. Let's go nums. I see. Is greater than 0, then that won't work either. Yeah, geez, how did we do it over here? Okay, so we did for color in my dictionary. We created some sort of index equal to this. We loop through I in range my underscore dic color. Interesting. So we loop through each color in the dictionary. Then we go for nothing in range mine. We go through the values. We make num's index is equal to color. Ow. Num's index is equal to color. And then we increment the index by 1 and we keep going. Could we sort the dictionary? How to sort dictionary? Sorted vowels is equal to dictionary sorted my underscore use a lambda function dictionary dot items key is equal to lambda. And we go item 1. That's not going to do anything actually. We want to sort it by item 0. Sort by key A. Simplified version. It don't like it. Whoops. Whatever. We sorted it. It's alright. Alright, back in a second. I'm gonna go to the bathroom, then we'll keep going. What's up? I'm back. Actually playing at 10 a.m. now, so we got some time. Let's jump into some more problems. Let's see what we got today. Take a look at a 2DP problem. How do we do editing distance? I feel like we sold that one yesterday. Might as well take a look. In two strings, word 1 and word 2, return the minimum number of operations required to convert word 1 to word 2. You have the following 3 operations fitted in a word. Insert a character, delete a character, replace a character. This is a DP problem. Convert word 1 to word 2. Replace H with R. Damn. This is a tough problem, bro. I don't have any intuition for this. Like I generally don't even know like even kind of like where to start, to be honest. Yeah, bro, the intuition is just not coming to me. Like I usually kind of know, like have an idea, okay, how I can solve this problem, but I'm actually not sure about this. Like I don't even know. Trying to think. Yeah, I am not sure, dude.
Life keeps changing, and Lovesack, it changes right along with me. On game days, I can get the most out of my setup. Lovesack helps me stay.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve edit distance. So this is a dynamic programming problem, and this is very similar to the problem longest common subsequence, which is a problem I've solved on this channel. So this problem is basically an extension of
We've done this one. How did we do this?
that problem. So we're given two strings, word1 and word2, and our goal is to return the minimum number of operations required to take word1 and convert it into word2. And we only have 3 operations available to us: inserting a character into word1, right? Remember, because we're trying to take word1 and convert it into word2. We can't change word2. We can delete a character from word1 because we can't change word2. And we can replace a character in word1. And so replacing a character is basically changing one character into another. So in this case, there's 3 operations it would take to take horse and turn it into this string. Of course, we'd want to get rid of the H, right? But we would do that by replacing the H with an R. So this is going to be an R. And then we have 2 R's, right? So we'd get rid of this R. So we get rid of that. And lastly, we see we have ROS, we have an extra E, so we're going to get rid of the E as well. So we did that in 3 operations, so we can return 3. So first of all, let's analyze some simple cases. What if we had the case where word1 and word2 were both just empty strings? How many operations does it take then to take word1 and convert it into word2? Obviously 0, right? We don't have to do anything. They're already the same. Similarly, if word1 was, let's say, ABC, and word2 is also ABC, we also don't have to do anything, right? We'd look at the first character, see, oh, they're the same, right? Since they're the same, of course, we don't have to consider them anymore, right? Then all we have to do is compare the remainder of each string, right? But then we see again, hey, B is the same, good. C is also the same, good. And look, perfectly timed. There's no characters left in word1 and there's no characters left in word2. Therefore, 0 operations were needed, right? What if word1 was ABC and word2 was empty? Then what would we do? Is it even possible to take this word and then convert it into an empty? Of course it is. In this problem, it's always going to be possible to take word1 and convert it into word2, right? Because we can insert a character, we can delete a character, or we can replace a character. So it's always going to be possible because in the worst case, right, this is what we could do. We could take every single character in word1 and just delete it. Delete that, because none of these show up in word2. Just delete all of them. If there was some character, maybe there's a Z over here, then we could just copy every character after we've deleted these and then copy it over here, right? Add that Z, but no, we don't need to. So my question to you is, if word2 is empty and word1 is non-empty, then this is a base case, how many operations is it going to take? It's always going to take the length of word1, whatever the length happens to be, because we're going to have to delete every single character, right? So that's one base case. Word2 is empty. What about the opposite case? What if word2 was ABC and word1 was empty? Is this possible? Is it possible to take word1 and convert it to word2? Of course it is, right? Because we're allowed to insert characters in here. So basically we could just read character by character. A, add that here. B, add that here. C, add that here as well, right? So we can just copy every character. So my question to you is, in this case, the opposite case, where word2 is non-empty, but word1 is empty. How many operations is it going to take? Well, we're just going to copy each character in here, right? So in this case, it's going to take the length of word2. That's how many operations it's going to take, right? So basically what I'm getting at is, if word1 is empty and word2 is non-empty, then we're going to return the length of this as the minimum number of operations. If the opposite was true, right, maybe this is empty but this is non-empty, then we'd return the length of the non-empty one. If one of them is empty, we're going to return the length of the non-empty string. That's going to be the minimum number of operations. This is important because this is our base case. So now let's try to brute force this. How are we going to handle it? Well, we're going to have 2 pointers, right? We're going to have one pointer pointing at a character in word1 and a second pointer pointing at a character in word2. We're going to compare character by character. So the one case is, what if they're exactly equal? Then what is the sub problem then, right? Because we don't have to consider these characters anymore. Now we're dealing with the sub problem of the remainder of those strings. So basically, if I'm calling the pointer in word1 I and I'm calling the pointer in word2 J, if these characters are equal, that means we can basically say I plus 1 is the new problem and J plus 1 is the new problem in word2, right? So we're just shifting our pointers like that. So basically, to summarize, if these characters are equal, right, at the I and j pointer, basically what I'm saying, the characters are equal, then we're just going to increment I by 1 and increment j by 1. The number of operations we had to do was exactly 0, right? We didn't have to do anything. They were already equal. We didn't have to modify word 1 at all. To the next character, so our I pointer is going to be over here, our j pointer is going to be here because we incremented both of them by 1. So now let's compare the characters. C and B are not equal, right? So now our else condition is going to execute, and we don't know. We know we have 3 options. We can insert a character, delete a character, or replace a character from word 1, but we don't know which one to do, right? So let's just try all 3. What happens if we insert a character? What character are we going to want to insert over here? Obviously, we'd want to insert the character from word 2. We don't know if that's going to end up making word 1 exactly into word 2 in the minimum number of operations, but let's just try it and see what happens, right? So what would we do if we inserted a C over here, right? We're not deleting a character. All we're doing is inserting a C over here. In that case, our I pointer is still going to be pointing at this B, right? But since we inserted a C over here, it's hard to read, but let's say I inserted a C in between over here, that means we took care of the C from word 2, right? So basically, we don't need to find a matching C for it anymore. We do need to find a matching B somewhere over here, right? So we're going to leave our I pointer where it is, but we're going to take our J pointer and then shift it to the next position in word 2. That's what we would do if we inserted a character. So as you can see, when we insert a character, we are taking one operation, right? So we're going to have to add a 1 to the number of operations we did. But when we shift our pointers, the I pointer stays the exact same, but J is incremented by 1. So that's one possibility. Another possibility is we delete a character. So we're allowed to delete characters from our word 1, right? So what would happen if I just deleted this character? What we're saying is, okay, I can't find a matching C in this position, right? And we don't have a B corresponding to that position. So I'm just going to ignore this guy, and hopefully the remainder of the strings can match up, right? So what I'm saying is I'm going to take our I pointer, and yes, I am going to shift it to the next position because I want to pretend like this character never existed. But it does take one operation to complete that. But since we did not find a matching C yet, right, we have to leave our J pointer here, right? We have to keep searching until we find a matching C. Ultimately, we want word 1 to match word 2. So in this case, for the delete operation, what we're saying is I is going to be shifted, but J is going to stay the exact same. So I plus 1, but J stays the same. As you can see, this is, kind of a pattern. We're starting to see a pattern, right? And the last thing that we can do is replace a character from word 1 that shows up in word 2, right? Obviously, if we're replacing a character from word 1, right, we're going to want the character that's matching in word 2, right? So what we'd want to do is take this B and replace it with a C character, right? If we did that, clearly these two characters match, right? We made them match. We forced these characters to match. So in that case, we know that the C has a matching C up here. So we can take this I pointer and shift it, and we can take our J pointer and shift it to the next position, right? So the replace actually ends up doing the exact same thing as if the characters were equal, and that makes sense because what we're doing is we're forcing them to be equal with the replace operation. The difference between the replace and if they were already originally equal is that the replace does take a single operation. If they were already equal, the number of operations it takes is 0, right? So it does come with a cost, even though replace is pretty powerful. As I said, with replace, what we're going to do is increment I and increment J. So let's just go with the replace operation because that's actually going to end up being the minimum solution. So now we shifted our pointers to the next position. We see D and D, they match each other. So this is the statement that's going to execute. And we know that takes 0 operations, right? So we're going to increment both pointers by 1. J is going to be over here now. I is going to be over here. Notice now how we have 2 empty strings. Remember the base case, if both strings are empty, we can return 0 because it takes 0 operations to make them equal, right? They're already equal, so we're done. We return 0. How many operations did it take? By the way, if you were counting, we did have to execute a single replace operation. That took 1 operation, so the result is 1. So we are noticing that the subproblems are good to solve before we try to solve the original problem of comparing the entire lists. Let me reformat this into the dynamic programming explanation.
This may be the last ad you ever see. Because with the free ad block extension from
You may have seen something like this before. This is going to be a 2-dimensional dynamic programming problem. It's good to visualize it kind of like this. So what we're doing here is we are comparing dynamic programming.
Interesting way to think about it for sure. Oh my god, I need to stretch my back. Oh man. Oh, my back is like so tight right now. Do. Def backtrack. We need an I. We need a J. Is that it? Really just I and J? I'm gonna do the brute force solution. If I is greater than time, if J I guess it would be if I and J, right? If I and J is greater than the length of word. We just return, right? Otherwise, we would do, okay, well, if word 1I is equal to word 2J, we would backtrack. I plus 1. 3 plus 1, right? Else. They're the same. Move. Right. We need an else if. Else. Backtrack. It's place. Oh, okay. If we were to replace, we would just do both. I plus 1, j plus 1. Probably wouldn't be a good. Maybe we would need count built in. We would add h, so we would go I plus 1, j, count plus 1. Then the delete would be j plus 1, sorry, I, j plus 1, count plus 1. It's the other way around. One string is exhausted. Okay, so this is the base case, right? So if I is equal to the length of word more. So if we've gone past everything, then we would return the length of word 1 minus j where we're at in j, and then we'd add the rest on. So all remaining from word 2. Okay. J is equal to the length of word 2, and we would return the length of word 1 minus I. Okay, so we got this right. If I is equal to word 1, I, word 2, j, we backtrack, right? else we would insert, we backtrack, then we'd want to return the minimum of insert, delete, place, the min of insert, delete, place. Got a little typo here, the insert here. I'm curious how we can do this DP problem here, because use memorization, I don't know how, like what, just the intuition doesn't come for me for this problem. Like we want to convert. Tried to convert word 1 to word 2, right? So in this case here, we come down here and we'd see H and R, right? So to insert, right, we'd keep I, but we'd increase over here.
Programming explanation. So you make a great B and replace it with a pointer and then shift it to the next position in word 2. That's what we would do if we inserted a character. So as you can see, when we insert a character, we are taking one operation, right? So we're going to have to add a 1 to the number of operations we did. But when we shift our pointers, the I pointer stays the exact same, but J is incremented by 1. So that's one possibility. Another possibility is we delete a character. So we're allowed to delete characters from...
I feel like he just doesn't really explain that very well. Like... How are we gonna add DP to this, man? Oh my gosh, dude. We'd have to hold the count, obviously, as the value, but I guess maybe we'd have to hold the key would be I and J. I feel like that's the only thing in this case it could be. So if I return DP IJ, so DP IJ is equal to 1 plus min Whoops. Trying to DPIJ. We'd return. Okay, DP IJ. You go to backtrack. I plus 1. Oh, sorry. No. There we go, dude. Okay. Let's take a look at some of the, like a hard problem here or something. Swim in rising water. That looks like a good one. Swim in rising water. Got a little bit of time here. Got a grid problem. I used to hate grid problems, but now I kind of like them. You're given an n times n integer grid where each failure grid ij represents the elevation of point ij. Rain starts to fall at time t, the depth of the water. The rain starts to fall at represents the elevation point ij. So what are we getting? We're just given a grid. The rain starts to fall at time t. The depth of the water is t. You can swim from a square to another four direction adjacent square if and only if the elevation of both squares individually are at most t. Of course, you must stay within the bound. I don't really understand this part here. Epitome of garbage. Find the path which has lowest maximum cell value. I don't understand how we're returning 16 though. I just don't get that. Only through cells less than. Eight, 9, 10, 11, 12. Okay, I understand. Okay. I understand the problem. So my initial intuition here is we could kind of use a queue. Okay, so Okay, let's think about this problem. So I think I'm gonna use Dijkstra's algorithm plus BFS here, right? So to do this, we're gonna need a min heap, right? I'm just kind of setting up the problem here because obviously we're gonna need a visited array, a visited set, right? We need our min heap. We need a queue, right? I think we'd need a queue. No. Okay, no queue. Our min heap is kind of used as the queue. I just forgot about that. Okay, so we'd obviously need a directions array to move, right? So we can do let's do like up, down, right, left, right? So to go up, we would go -1. To go down, we would go that's +1. To go left, we would go -1. -1, 0. To go right, we would go +1, 0. Let's go left, right. Okay. Probably would need to append our first thing here. So let's do min heap. Heap dot append, and we append 0, 0, 0, right? So first being the weight, then being the x and the y, right? Okay, so here we would probably have to go while min heap, right? We would want to pop, right? So we pop our weight, we pop our x, we pop our y, which is equal to heap q dot heap pop, and we pop from min heap, right? We pop our shit, right? Which we, using our min heap, we always pop our lowest number, right? So we pop our lowest, and then what would we want to do here? We would we want to check if it's in visited, right? So if if x, y in visited, we'd simply just want to continue, right? And then we'd add visited.add. We want to add x and y, right? I think that's important. Okay. Then we'd probably want to do for new row, new column in. Sorry, let's do for CR. Current row, current column in. Sorry, for new row, new column in directions, we want to do new row is equal to new col is equal to, we would do, okay, well we do x plus nr, y plus nr. Then we have to check the bounds, right? So we would go, okay, so if 0 is less than or equal to new row, but is less than, I guess I didn't think about it. We didn't, rows is equal to the length of grid, and our cols is equal to the length of grid 0, right? We'd want to check if it's in bounds. New col less than cols. Okay. And let's do new row, new col not in visited, right? Then we would append to our heap. So we do min heap dot append, new row, new col, and then obviously the current weight too. So we would need to do would be, I guess, our weight plus grid, new row, new col. I think that would be the way to do it. Since we have a min heap, we're sorting it based on weight, right? So we're always going to take the lowest weight, right? So here, the lowest weight. All the way down. And then we'd get to here. We do, okay, if how would we check if x is equal to rows minus 1, x is equal to rows minus 1, y is equal to cols minus 1, and we've found our option, right? We would simply return the weight plus weight plus 1. Let's just return our weight, right, for now. Here we'd have to check, okay, we're gonna have to do something here, right? Because if the grid is greater, we have to wait till then, right? But if it's less than, we can just add 1, right? Or then we don't add anything, right? Because at that we can move in 0 time. So I think we would have to go if grid, new row, new col is greater than weight, right? Then we'd append like this, right? Else, if it's not, we would append min heap dot append w, new row, new col. Okay, then we'd probably want to return our weight. Here we'd probably have to do the same thing. So we'd have to check, well, if grid x and grid y is greater than weight, then we'd have to return weight plus grid x y. Else we'd probably have to return just the weight plus 1, right? But it's not grid x y, right? Because if we go here, we would just have to wait till here, right? So I don't think it would be plus this. We would return grid, new row, new col, right? And we'd probably do the same up here. Maybe we wouldn't even have to do the wait then, technically, because we go here, we get to 16. If it's higher, but if it's less than, right, then we're just returning 16 the whole way. Technically, right? So I don't even think we need this, because we're just returning 16 the whole way. Once we get to 16, then it's less than. Else, if it's less than, I think you're right. If it's less than, then we just pretty much return the weight, right? Fuck, man, this is confusing me, dude. If it's greater than the weight, we return that. If it's less than that, this is technically still 16. I think it would still work. Then we would just return our weight, right? Otherwise, if it's greater than, we would return grid x, y. Okay, let's see how this goes, dude. Takes exactly 3 arguments. Okay. Okay, we're not even returning anything, so that's probably not good. Case 23. Let's see what this says. You're very close. It's a small bug in the way you're calculating new call. Oh, this needs to be NC. Whoops. Heap Q, I've got to do this. Heap push. Min heap. Min heap. Dude, all these parentheses are pissing me off, dude. Like, so confusing. Like, okay. There we go. Does this submit the wrong answer? Oh. Okay, so they're also saying here that I have redundant logic when I'm checking here. Instead of this, oh, it's because I'm starting. We're not starting at grid 0, 0. It's not always 0. There we go. Wow, we did a hard problem. That was actually, I mean, I know we had a few bugs at the end, right? But, you know, we did 95%, 98% of that problem, right? Like, that was pretty much one of the first hard problems I pretty much solved all by myself. So that's a good milestone to have. But I'm going to call the video there because I got to start getting ready to leave. So I appreciate you guys watching. I might come back and do a little bit more when I get back. If not, you know, I'll still edit it at the end and, you know, have a little outro or whatever. But I might be back to do some more problems later. So I appreciate you guys watching. I will see you later. What's up, guys? It's about 4 o'clock now. Back from my pickle. had to take a nap, recover a little bit, till I could jump on the computer and start doing some stuff properly. And I have. But I'm back. I was thinking, you know, maybe we can jump into one problem. Just to make the video a little bit longer. Just why not? I was thinking of the linked list problem. I feel like it's been forever since we've done a linked list problem. But we do a lot of them. So, sign Twitter. I think we've literally done like all of the linked list problems though. Merge case sorted lists. Let's take a look at this problem or something. From the head of a singly linked list where elements sorted in descending order, converted to a high balance binary search tree. Okay, we're given the head of a linked list. We need to return the tree node. How do we know that it's 0 though? What is high balance? I'm thinking, like, since we don't know where to split, You know, to be completely honest, I don't really know how to solve this problem. My intuition here is giving me some sort of recursive algorithm, potentially. But I don't know if that's right. I think that's probably wrong. I don't feel like it would be... Sort of list is similar to an in-order traversal of VST. We could kind of see that. Always choose the middle element of the list as the root. Okay. Okay, so we're told here to use recursion and use a fast and slow pointer to find the middle point, right? So, how? So let's first do our fast and slow pointer, right, to find the middle value. How do we do that? Well, we would do while head. I guess we do fast. I'm getting a call, dude. Oh wait. Let's do slow is equal to head, fast is equal to head. While fast is not equal none, right? What we want to do is we want to do slow is equal to slow.next. Fast is equal to fast.next.next, right? We should print our list node val 0 next. I believe this should be right. But I don't know how we would do recursively. How would we do it recursively? So they use a prev node. Alright, so for some reason they have a prev. They cut the list. If prev.next is equal to none. So I guess they're cutting the list to divide the list into two halves, right? That's what I'm thinking. So we check, okay, well, if we have a prev, then we want prev.next to be equal to none. Okay. Now we would do the recursive part, right? So the recursive part is, well, root is equal to tree node slow.val, right? Left is equal to, I feel like we started head, right? head if slow does not equal head, else none. Now let's study why this is the answer. I'm not sure here. Slow is middle point, right? But here we're recalling our function here, passing in head, right? If slow does not equal head. I think the right is easy because with root.right, we're literally just passing in self.sorted this to bst slow.next. Okay, because we're at slow, we're passing in slow.next, right? But here not prev is equal to slow. I thought we made slow.next is equal to null. Here we'd simply turn our root. None type has no attribute val. This is, I think, what we need a base case. What we do, okay, well, if not head, then I think we just return, what will we return? None. If not head.next, turn tree node head.val. Right, so we have a couple base cases here. Okay, I understand this, but I don't understand this part. I want to see the test case. Okay, we're gonna leave it at that. I think I understand, but I'm not 100% sure. But definitely something to come back. I am definitely very tired, so. But yeah, we're gonna call it there. So I appreciate you guys watching, and I will see you guys tomorrow.